Hello everyone. In this video, we are going to talk about KNN, K Nearest Neighbors. KNN is a classification algorithm and does the task of classification in a very specific and unique way. In this video, we are going to learn what that unique way is and also use two examples to learn about the tuning and also the many different aspects of this algorithm and how we can use this algorithm for a successful prediction. Alright, in this video we're going to use two data sets. The first data set is customer loan.csv and then customer subscription.csv. The first data set is very small and we're basically using it to talk about what KNN is. And then the second data set is a bigger data set and is more towards the side of being a real data set. And then we use that data set to actually do some meaningful classification in a real world example. So first thing we always do, we import our packages and we read our customer loan data. And we can see the customer DF is a very small data set. It only has 4 columns and 20 rows. So it's not going to be very hard to get to know this data set, but let's go ahead and do that together. We can see about the numerical attributes in this data set and their mean and standard deviation, and also we can use the bar charts and the histograms to help us get to know these attributes better. We can see income between 80,000 to 120,000, and the score, which is the credit score, is between 680 to 820, around these two numbers. So we can also see the relationship between our attributes. If we were to do a scatter plot, we do see that there is not much of a correlation between the income and the score. And if we can also do the correlation, we see it's around 20%, which is not that high. We can also see the relationship between the numerical attributes and the categorical attribute. Our categorical attribute here is the fact that if the customer were in default or not, right? So there was a default in the loan payment or not. So that's the categorical attribute. So we do visualization to see that actually the income has a strong relationship with a customer being in default or not. And also we can see that income also has a strong relationship with the customer being in default or not. So this actually presents a perfect data set for classification. We have two attributes, two independent attributes that are not highly correlated with one another, but both of these attributes do have a strong relationship with the class label, which is if the customers are in default or not. So this is a perfect example of a data set for classification. So we are going to create a classification model so we can predict default or no default, or customer being in default or not, for based on their income and credit score in this data set. So we also want to, once we create our classification model, we want to be able to have a prediction for this new customer. So if I were to draw the whole data set in one diagram, I could do it this way. I have the blue dots, which are the no default data. We can see that they have a higher credit score and also they have higher income. And then we also have the orange dots, which are the customers who are in default, who have been in default, right? And there is this new customer, and based on this 20 data set, the customer that I want to come to a classification or a prediction for this new customer. So that's what we're trying to do. And with K nearest neighbors, all k nearest neighbors algorithm does, it says, okay, let me find k neighbors to this new or this data object I want to have a prediction for. Let's say I want to find 3 neighbors. So I find these 3 neighbors, the point 1, 3, and 4. And then based on these 3 neighbors, I will come to a conclusion, right? So since there are 2 neighbors that have no default, and there is 1 neighbor that has default, I probably can predict that it's a default, right? So that's the whole KNN algorithms, k nearest neighbors. But let's do this, in a methodical and algorithmic way instead of doing it visually. So the first thing we need to do is to standardize our data. The reason is KNN uses distance, and the value of the distance is consumed or is affected by the unit of the measurement. And since the income has a larger unit than the score, we need to make sure that our data is standardized before applying it to our algorithm. So we do the standardization. We don't forget that we need to do the standardization both for the training data and the new customer. So that's what we've done here. So once we do this, now our data is prepared. So let me go ahead and actually show the new training set, which is, you can see that the value, the data is, there has been a transformation of the data. And I can also run the function describe, and the function describe will show us that the standard deviation for both of these are very close to 1. Alright, now that the data is ready, now we can find the nearest neighbors. Here we are using the nearest neighbors function from the sklearn.neighbors module, and all we need to do, we create the model, we say we want 3 neighbors, as in we want to find 3 neighbors, and then fit our data to the model, right? So that's all it's been done here. And then this knn.kneighbors will return the closest neighbors, the closest 3 neighbors to this new data object. Now we can see 14, 1, and 3, as we had seen in the visual, are the nearest data. If I had changed this to 2, then I would be getting 14 and 1, because those are the closer ones, and so on and so forth. So I recommend that before moving forward with this video, stop and play with this number a few times and see the range of different results you will get. And now that we did see 2 of the the neighbors, we can also use another module or another function, which is Nearest Classifier. This is a different function. This is a function that nearest neighbors is only giving you the just only finds you the nearest neighbors. This one actually finds the nearest neighbors and derive a classification from those nearest neighbors. So this is a one step further than what we already did in the previous chunk. So here we not only do that, we say we want 3 neighbors, and we fit our X and Y data, we also drive our prediction. Once we do that, our prediction is no, as in the customer is not going to be in default. And we can see that if there are 3 neighbors, this is going to be the prediction or the classification for this one, because 2 of the nearest neighbors are saying no, and 1 of the nearest neighbors is saying yes, and 2 to 1 prevail, basically. So this was just to show you an example of KNN, right? So to understand how KNN work. But this is a very simple and small data set. Now let us bring our focus to a second data set that we can use to actually do meaningful classification here. So here we are going to use the data set customer subscription.csv from this Kaggle page, and you can go ahead and look at this Kaggle page. The description of the attributes are provided in this Kaggle page. So if you are interested in probably you will need throughout this video to be able to look at those attributes. So why don't you go ahead and open that web page, so it's handy, you can like refer to it if you need to. So this data set has 16 attributes, and some of them are categorical and some of them are numerical. We separate the categorical attributes so we can more effectively get to know all of the attributes. So the categorical attributes are job. We can see different types of jobs in this data. We have marital status for the customers. We have the education for the customers. We have the if they have had default or not, and we look at the if they have had loan or not, and what the type of contact we did for them for this marketing campaign in this data set, the month we did this campaign, the day of the week that we have been contacting, the last time we have contacted the customer, and if the customer decided to subscribe or not, right? So these are the categorical attributes in this data. We can see for most of these attributes there is an unknown category for all of these categorical attributes, unknown. So we go ahead and change those unknown to a non-value, right? That np.nan, because those are not real classes of our data. So this is basically a missing value. So we go ahead and change those things to missing values as they are, and then we there are the bar charts, and we can see that these bar charts now do not have that unknown attributes in them. All right, now that we have looked at the categorical attributes, let us take a look at the numerical attributes, which we have age, duration, campaign, previous, and p dates. And once we run these, we will see that most of these attributes are in a wide range of numbers, especially the age, and then you have duration of the campaign, the campaign, number of campaign, and the p days, and so on and so forth. So why don't we go and check the description of these attributes from the Kaggle page. So if you open the Kaggle page, we will see that, for example, duration is the last contact duration in seconds. It means how was the duration of the contact with the customer. And the campaign, number of contacts performed during this campaign, number of contacts that so the first one is duration of the last contact, and this one is how many times we have been in contact with the customer. And then p days is the number of days that have passed after the client was last contacted. So these are all three important attributes for what we are seeing as the last time we contacted the customer. And the previous is about the number of contacts performed before this campaign and for this client. And then P outcome, or previous outcome, is the outcome of previous marketing, right? So these are the numerical. This is not actually numerical. This is a categorical attribute that we saw in the other one. And the Y is the outcome of this campaign. So now we understand better what's duration, what's campaign, and what's previous, and P days, the number of days that have passed from our previous contact. So if you look at P days definition here, you can see that the number 999 means client was not previously contacted. So this is also another form of missing value. So instead of using the number 999, why don't we go ahead and just put it as a missing value as it should. So we replace that, and once we do that, now the p days attribute has sort of, it shows its variation here, right? Do you see it was just like a one bar in the histogram here, but now because this is eliminated, now you can see its variation here. So next thing we do when we are getting to know a data set, after getting to know each attribute, we are also interested in getting to know the relationship among these attributes. So we do a matrix, scatter matrix with the SNS pair plot for all of the numerical attributes, and also we do a heat map for the categorical attributes, the pair of categorical attributes. So once we look at these figures, we see that there is not a stark relationship among these numerical attributes. We could not say there is a significant relationship among them that could be troublesome. And then we look at the relationship between the categorical attributes, and there are a good number of them, but we can see there are some relationships. So for example, there is a relationship between education and job. And there is a relationship between default or job, having default or not, and so on and so forth. So you want to have looked at these relationships, especially for the next step that we will be performing for the task of feature selection. Because when we are doing feature selection, we have two goals. We want to have first the most amount of relationship with the dependent attribute or the target, but at the same time we want to have the least amount of data redundancy, and high correlation shows us a possible redundancy in the data. And also we draw the relationship between the numerical attribute and categorical attributes. To do that, we need to first dumb down our numerical attribute, as in we need to transform it and make it become an ordinal attribute, so we can now draw the heat map for them. And once you do that, you do see that there are also some relationship between these attributes that you want to have studied and know about them. So take some time to go through these visuals. After properly getting to know the data, now it comes time to pre-process the data for the classification task. Here we want to classify the data object customers to either subscriber or not subscribers, and the possible predictors or independent attributes that we have are listed here. And our dependent attribute is Y, or the fact that if the customers is subscribers or not. So one of the things that we need to do for this to be successful is we need to make sure that all of our independent attributes are presented in numbers. As we saw, KNN uses distance as a way of classifying the data object, right? So we have to make sure that all of the attributes are presented in numbers so KNN can work on them. To do this, we use pd.getDummies, which basically replace any categorical attribute with binary codes. So the drop first true is basically saying that for a category, for attribute that has 3 categories, you need only 2 binary codes. For an attribute you have 4 categories, you only need 3 binary codes, and so on and so forth. One of the things that we need to do before moving forward is to deal with missing value. Largely, KNN is capable of handling the missing value itself. And the way it does, basically, when there is a missing value in the data, it does not use that attribute in calculating the distance between that and the rest of the classes, right? So that's how KNN can deal with missing values. But there is a specific type of missing value in this data that we need to actually do something about it. Specifically, the missing value that we talked about, let's see, where was it? The missing value for previous P days or previous days, days from the past contact with the customer, we switched the missing value from 999 to missing values, right? So that's what we did. But now we want to do something about that. The difference between this missing value and the rest of the missing values are the fact that we did not know the information about those situations, right? But here we do know that there is no information to have because we did not contact these customers. So we know what happened. It's not like we don't know. it's that it's very different and it doesn't apply here. So in these cases that we have such cases that the fact that the data is not there is also important. The way we go about dealing with these missing values is by using the double M method. In double M method, basically we want to find a big enough but not too big number to replace instead of these missing values. So there is that distinction between these values, the one that we don't have, and the rest of the data as far as the distance that they can create. So the double M stands for max mean method. Basically, in this method we fill the missing values with the maximum and the minimum, and the maximum and the mean, maximum plus the mean of the attribute. Once we do that, we will see that that distinction is created here, while not with a number such as 999 that would consume the space of distance for this attribute. Of course, before moving forward, we also need to do standardizing our data. So we do that by using the standard scalar of scalar module, and once we do that, we check that all of the standard deviation for all of our data now is 1. So that's the goal of standardizing the data, which happened here. Of course, when we want to do a classification such as prediction, we need to also make sure that our prediction is evaluated. And the way we evaluate prediction, such a classification similar to prediction, is to use the train test mechanism. Here we split the data into 4 chunks, and now we can sort of like use the test set to see if the algorithm is doing any good, basically. And also we need to do some feature selection. If you haven't watched my video on feature selection and dimension reduction for classification algorithm, go ahead and watch that video. And so we covered 4 methods here, for 4 methods in that video, but here we're only going to use one of them, which is the random forest. Once you run the random forest algorithm basically uses a number of estimators. Here we have 1,000 decision tree algorithms, and these algorithms are being used in a random way, and because it's random, every time the attributes that are used for classifications are different. So the attribute that is used more often is shown to have had more influence on the classification of the dependent attribute. And once we get the output and the result here, we will see that the duration, age, campaign, and so on and so forth have a value and importance in prediction and classification of the subscription. So let's use the rule of thumb, not the rule of thumb here, let's use the cutoff point of 1% as it being enough to stay for our classification here. So when the importance of the attribute is higher than or equal to 0.01%, we 0.01 we use the feature, otherwise we discard it. So these are the selected features that we're going to be using for this classification. So now that we have the selected features, the X train, Y train, XS, Y test, now we can go ahead and use K-neighbors classifiers and do the classification here. Once we do that, we will have a prediction for all of the members of the test set. Now, once we do that, once this is run, we can do a contingency table to see the performance of our classification. So now we draw a contingency table. The X or the rows here are the actual case for these data objects, and the Y's here are the prediction. We see that the algorithm is doing well with predicting who is not going to be interested in subscribing, but it's not doing as well on who is going to be subscribing, which is something that is more important, because we are doing this classification to sort of like target our marketing scheme and marketing efforts towards those customers who are more likely to subscribe, right? So that's one way of looking at the evaluation of classification algorithm by looking at the contingency table, but there are also metrics that we can use. The metrics that you can use for binary classifications are accuracy, recall, precision, and F-score. And this is all of them are calculated here. So by running this, we can see that the accuracy is around 90%, which is a fair number, right, for accuracy. But the reason that the accuracy is high is because there are a lot of nodes in the data, right? So that's why that's what's the case. But it only shows itself as not being really that impressive when you calculate the recall and F-score. That tells you we are not really doing well in the prediction of the positive cases or the yes cases. So now here we create a function to keep doing this, to be able to keep evaluate the metrics, because the next step is going to be for us to tune ANN, right? So now we want to make sure that we can tune the ANN. One of the things that I want to point out before moving on is the fact that with any algorithm with classification or prediction, you could tune your algorithm based on different metrics, right? So a lot of times the metrics that are used for tuning is accuracy. But in this case, because what is important for us is the recall, because we don't want to make as much false negatives. So false negatives are costlier for us in these cases. We are going to focus on tuning recall. Right, so that's what we are going to do here. But there are two parameters that KNN can use for tuning. The first one is, of course, the number of neighbors. The second one is the way that the algorithm makes that final decision. So when there are neighbors, between the k nearest neighbors, every time we have some of them as one class and some of them as the other class. The way the KNN algorithm works, when the weights is uniform, each of these k nearest neighbors have the same amount of vote, or they will get only one vote, right? But when the weights are set as distance, the closer the attributes, the closer the neighbor to the data object that we want to classify, the higher their weight in the final class or final. Since we only have two attributes here, we can go ahead and tune them at the same time. So we further split our data into train set and tune set or validation set, because we don't want to tune our data to the test set, which is a common mistake that might happen, but that's something you don't want to do. You want to always keep the test set separate throughout your planning and tuning of your algorithm. So that's what we don't do here. We have a train, tune set, and then the test set. So we use the tune set to find the best parameters for this algorithm. We created TuneDF, which is a placeholder here. One of the things that I want to point out here is the fact that KNN is not a random algorithm. That's why you're not going to need more than one repetition. So that's why we only have one repetition here. And once you have this set up, now you can create a algorithm or create a nested loop to go about doing the tuning. Basically, you have to computationally experiment with KNN and see which combination of these parameters will lead to the best. And the metric we're using here is recall. So metrics is the output of the function that we created, and the second output, if you remember, was recall. So that's why we have put 1, because the first one is 0 and the second one is 1. And we put that in our placeholder. And number of neighbors and the weights comes from these possible options, and the number of neighbors we are going to use is from 1 to 9. So now that everything is set, I'm going to click run. This is going to take a while, so I'm going to fast forward the video once I do that. Okay, now that this is done, we can sort the performances, which are recalls, based on the descending order. You can see that the number of neighbors 1 and the uniform leads to the best performance. But one thing that you want to pay attention here is the fact that these three parameters or combination of parameters are actually the same thing. Think about it for a minute before moving forward. That's why these are the same thing. These have the same performance. But once we have that tuned model, now we want to put our tuned parameters and then use the whole X train instead of the smaller part of X train for the training, and then using that for the prediction. So once we do this, now we can predict the test set. Now we are predicting the test set, and we see that the recall has improved, and also we check that we have many more numbers of yes cases, and that's promising, because using the tuning, we're able to improve the performance and the performance metric that is important for us to improve that, basically. Before finishing this video, I'm going to compare the performance of this algorithm to a random classifier, right? So I go ahead and create a compare df, which basically compares, create a table to compare these two methods, random and KNN, with on accuracy, recall, precision, and FS score. So the KNN method, we have already run this, so the predictions are saved in this variable. So we have the prediction and they have the y-test, and we calculate the evaluation metrics and put them in the compare df. And then on the random method, we create a prediction with one consideration. The consideration here is we don't want to have more than one prediction of yes subscriber, because if it did that, then it would favor the random, because you have more chances of predicting yes, right? So the more you could say yes, the better it's going to be for you to have a better recall. That's why I have come up with this line of code, basically randomly come up with 0 or 1, but it comes up with more 0 than 1. And the number of ones that it comes up with is exactly the same number of ones that this predict y had come up with. So once we run this, we will see that the KNN algorithm is by far doing much better than just randomly selecting these customers and calling them. This classification algorithm were able to improve our decision making by around 30% than of us just randomly choosing customer and calling them, which is an improvement. Alright, so in this video, we first talked about what is KNN. Now we saw KNN in a very small data set. Next, we made it a little bit more challenging by making our data set more real, and then we talked about different aspects of KNN and the fact that the KNN needs to have the data standardized, and also the fact that it needs to have all of the data represented in numbers. Also, we talked about the needs for tuning, and we showed that with the proper tuning, we have the capability to select a metric and tune the algorithm in a way that is going to help us improve the algorithm based on that tuning. And then we saw that at the end, the algorithm did much better than just randomly classifying